My presentation will be about stellar evolution. So, the definition of a star is a collection of plasma held by its own gravity. Plasma is the fourth fundamental state of matter in which gas dissociates into ions due to high energy, and it doesn't actually exist on Earth. The lifetime of a star is all about balancing its own gravity that pushes itself to contract with thermal pressure generated by some kind of energy source. This energy source is usually fusion, but it varies in the star's different stage of life. Star formation takes place in a dense region with molecular clouds, usually inside a nebula. These molecular clouds might be the remains of a supernova explosion or a decaying red giant. Often triggered by collision or radiation from massive stars, the clouds begin to contract and reach a sufficient density that satisfies what's called James instabilities. It becomes unstable and collapses under its own gravity. At this stage, fusion hasn't started yet, but the thermal pressure resulted from the gravitational energy put it back to hydrostatic equilibrium, and a protostar is formed. As the thermal energy keeps increasing, fusion finally started. The star is said to be on the main sequence of stellar evolution, during which its percentage of helium and the rate of fusion both increase. A star spends 90% of its lifetime on the main sequence. To understand what a main sequence is, look at the HR diagram to the left. The main sequence is actually a continuous central band of stars that appears on this plot of color versus luminosity. The stars in different bands are usually in different stages of life. So since our star has entered the main sequence, its fusion mechanism begins to take the following forms. The first one is the proton-proton chain, which usually happens in stars that has less than 1.3 solar mass. In this chain, two protons bump together to form a deuterium, which is an isotope of hydrogen, and the deuterium absorbs a proton to form helium-3. Finally, an alpha particle is formed by fusing two helium-3s together. The second one is the more complicated carbon-nitrogen-oxygen cycle. It's basically a carbon-12 undergoing proton absorption and electron emission to form nitrogen, oxygen, and their other isotopes, and finally goes back to carbon-12. Since this reaction requires the presence of heavier elements, it only happens in stars that are heavier than 1.3 solar mass. The next one is the alpha process, in which alpha particles fuses together to form heavier elements. For example, carbon-12 in the second reaction is generated in the first place by fusing three alpha particles, called triple alpha process. In a massive star, the alpha process allows the elements to keep fusing and climb up the ladder of atomic number all the way till it forms iron, which has the lowest nuclear energy. These several types of reaction are held together by the shell forming and burning process. At the end of a star's main sequence life, enough helium has accumulated so that they sink into the core. Same for carbon. A carbon formed by triple alpha process will also form layer when they accumulate enough. A massive red giant will look like an onion with shells of hydrogen, helium, nitrogen, carbon, neon, silicon, and iron from the surface to the core. The fusion of specific element is called burning. Burning is not the alpha process. The burning of different element each has its own set of reaction that forms other stuff. As the star ages, the helium burning will happen first, followed by carbon burning, neon burning, etc. To wrap up the relationship between fusion and stars, the older and larger a star is, the more types of fusion it will have. It performs hydrogen core fusion during the main sequence lifetime. For example, our Sun is at this point on the HR diagram right now. When it runs out of the hydrogen field, it becomes a subgiant. Helium will start burning at the core, and the remaining hydrogen will keep fusing at the shell. This stage is called the hydrogen shell fusion. We'll see a horizontal move of the star on the diagram. A carbon core will form when the star becomes a red giant. The size of the star grows because the extremely high thermal pressure it releases from fusing heavy elements is able to overcome gravity and expand the surface. And since the surface is now further away from the core, we'll see a decrease in temperature and the presence of a reddish color. Finally, our star reaches the end of its life. The temperature becomes so high that even iron starts fusion. But as you know, iron has the lowest energy level already, so when it undergoes fusion, it actually absorbs energy instead of releasing. There's no more thermal pressure to counteract gravity so that the core collapses. All of the outer layers get blown off from the star, and this is a supernova explosion. In fact, this explosion is more than a blowing up process. The creation of elements after iron is attributed to supernova with its intense emission of neutrons. These neutrons, after flying out of the iron core, are captured by surrounding nuclei, and then decay to proton by emitting electrons and an antineutrino. Each captured neutrons will cause the atomic number of that nucleus to go up. After the explosion, the star might end up with a white dwarf, a neutron star, or a black hole. But that will be another story unrelated to nuclear reaction. So this will be all of my presentation. If you have any question, please ask me during class.